Today, I'm interviewing Reiner Pope, who is CEO of MatX, which is a new chip startup. Previously, he was doing TPU architecture and many other things at Google. This is a very different format from my usual interviews. This is going to be a Blackboard lecture. We're going to get up in a second. We, in fact, built this whole new studio with specifically this format in mind. And so it's a pleasure to get to inaugurate it with you. We're going to be talking about model architecture, ML infra, and many other things. And the reason I think it's an important topic is because once you actually understand how training and inference actually work in a cluster, as we'll see, a lot of things about why AI is the way it is, why AI architectures are the way they are, why API prices are the way they are, fundamentally also why AI progress is the way it is, start making sense. And you need to understand the details to get there, and you need a Blackboard to understand the details. So Reiner, thank you so much for doing this.
Yeah, very happy to be here.
Okay, full disclosure, I am an angel investor in MatX, but that's not related to this podcast. Reiner, maybe to kick us off, I'll ask this question. So we have a couple of companies like Claude and Codex and Cursor are offering something like fast mode, where for 6x the price, they'll stream you tokens at 2.5x the speed. Mechanically, I'm curious what's going on here. Why is it the case that you can pay more to get faster latency? And two, could you keep going? Could you pay 100x more and somehow get even faster speeds or much, much faster speeds? And three, could you go the other way? Could you have something like Claude Code slow mode, where if you are willing to wait for minutes on end, you could get even cheaper prices? So maybe this will help motivate the kind of analysis that you'll be doing through the lecture.
Great. I mean, to jump to the conclusion, the big effect is batch size, but what we're going to do now is quantify exactly what that looks like and what its implications are on latency and cost. There's going to be another effect, which is, you can call it speculative decoding or multi-token prediction. We can maybe come back to that later, but I think the first thing that we'll talk through is batch size. So what I'd like to introduce is sort of the two principles of analysis. Firstly, we're going to look at a roofline analysis of how I run a transformer model on a cluster of chips. We'll take a sort of let's say a Blackwell NVL72 cluster, so a rack of 72 GPUs. And so the roofline analysis means we look at memory bandwidth and compute performance. And then the other side of that is that we're going to look at just two simple factors of the model, which are the time to operate on the weights and then the time to operate on the context, the KB cache. So let's jump in. What we're going to try and do is we're going to try and estimate the time that it takes to run an inference of a certain shape. Now, we're not perfect here. We can't exactly predict the time. And so instead, we're going to approximate. And so we're going to say that the time must be greater than or equal to a certain quantity. And so we're going to consider two different aspects. We're going to look at the time for it takes to do the memory fetches, and then the time it takes to do the compute. And it'll turn out that this actually gives us a very strong predictive power, even with this simple model. So one by one, what is the time that it takes to do the compute? So there are really two things I need to do in the compute. I need to multiply by all of the active parameters. And then I need to do some work on the attention. So multiplying by all the active parameters, I have a certain batch size that I'm running. And then I've got a number of active parameters in my model. And then I'm just going to divide this by the compute throughput, which is the flops of the chip. So this is a hardware constant. So this actually accounts for all of the compute time for all of the weight matrix multiplies. There's a little caveat here. We've sort of ignored the time to do any of the attention computation, but that in general will be quite small in comparison to this. So we'll ignore this.
Maybe I'll just interrupt from time to time to ask some very naive questions or to clarify some basic points. But just for the audience, you're not serving one user at a time. The batch refers to the fact that you're serving many different users at the same time.
Yeah.
And that's a whole batch.
Yes, I can motivate the batch at least a little bit. So, I mean, we will see exactly why batch is such a favorable optimization. But what will turn out to be the case is that if you do not batch together many users, the cost and the economics you get can be like 1,000 times worse than if you do batch many users together.
Yeah.
And we'll be able to see that quite explicitly. Yeah. And then number of active parameters, this is saying, like, if I look at, for example, a DeepSeek model, the DeepSeek V3 model has about 37 billion active parameters and then 700 billion total parameters. So this is, we're focusing on just the ones that are active for a single token. Okay, so we modeled compute performance. I'm going to keep writing equals, but in all of these cases, you can think of this time as being at least this much, and maybe there'll be some terms we ignored. On the memory side, what do we need to do with memory? We need to fetch all of the weights, and so there is some time to fetch all of the total number of parameters, not just the active parameters. So there's weight fetch time, and then in addition, there's a 𝐃𝐕 cache fetch time. So there is, this actually depends on batch size. So for every element in the batch, we have to fetch an entire context length worth of tokens. And then there's a size per token. So like bytes for one token. And so this is a model parameter.
And maybe just back in, let's just explain what the 𝐾V cache is real quick.
Yeah, so when I do a forward pass, let me draw actually how the autoregressive inference works. So this is during decode. So if I think I have a bunch of tokens of text, I'm drawing a tensor because ultimately the tokens are represented as some like tensor of in some embedding dimension, and then in this direction I have the sequence length. The work of running a decode is I have to run each token through a whole bunch of matrix multiplies over a bunch of different layers, and I have in general I'm going to have to do that work over all of these tokens. But then one step of decode is actually to produce just this one additional token out here.
Yep.
And so what I'm going to do there is I'm going to run a full forwards pass of multiplying by all of the weight matrices in the entire model. But then I've got this attention mechanism where this token sort of, it's like looking at all of the past tokens in this way. And what is it looking at specifically? It is looking at some internal representation that the model has produced of the tokens, and we call that the 𝐾𝐕 cache. So this process of attending, this single token attending to all of the history of tokens, that's attention. It is mostly dominated by memory fetches rather than matrix multiplies. So we've got the amount of memory that we're fetching shown over here, and then this is of course just then divided by the memory bandwidth. So the memory bytes per second. So in fact, these equations here are actually enough for us to now draw some fit lines. And so the things that we'd like to look at are sensitivity to batch, and then also, which we'll draw separately, to context length. So we said that the big effect you can get is like some trade-off in latency versus cost in batch size. So let's draw them out. I think there's just really two graphs we want to draw. We'll first just draw batch size versus time here. So when we look at the shape of this, we've got a maximum of, well, the sum and then another term. So let's look at these terms one by one and how they scale the time for compute and memory and how they show up. So let's first look at this compute time. This is just purely linear in batch size with no offset. So it is some curve like this. This is T compute. And then on the memory side, we've got some portion here that is just this constant that is constant in some base offset here, which is the weight fetch. Weight fetch. And then finally we have this term here, which is the 𝐾𝐕 fetch, which we're going to draw as this is the 𝐾𝐕 fetch, which is linear in batch size. And so it looks like that. So the sum of this plus this maxed with this. So let's at least first draw the sum. So the two memory times in conjunction end up looking on this curved slope like this. And then we get the overall maximum is, I'll draw a little thicker here, is the maximum of these two curves.
Makes sense.
Okay, so what does this mean actually? So this is a latency plot. So if I grow my batch size, I get initially some not very strong dependence on batch size. And so there's some lower bound on latency here. Latency lower bound. Lower bound. So this already partially answers the question. For a given hardware configuration, and then we can talk about varying the hardware configuration, but for a given hardware configuration, there is a lower bound on latency, which is simply I need to read all of my total parameters from memory into the chips. And that takes a certain amount of time. If I use all of my memory bandwidth, I can't do any better than that.
It seems like the way you've drawn the slopes for compute time and how the 𝐾𝐵 grows, and what implication the 𝐾𝐵 has on memory time, that as
what if this were above or below, or
or is that necessarily the case? Because if this is always true, then as batch size grows, compute always dominates 𝐾𝐵, and which suggests that if you have big enough batch size, maybe memory is never an issue.
Yeah, this is really sensitive to the context length. So I think we should come back and explore this. There will be, as you vary the context length, the 𝐾𝐵 fetch time will go up and up. And so that'll cause a transition from compute limited to memory limited.
And is there something especially significant about the slope being exactly the slope of the compute time?
Yeah, whenever we have balance points, it kind of says that you're getting it exactly right. And so for the particular context length where the slopes match, that says I am equally memory bound and compute bound, which is a really desirable place to be.
But suppose it's like, this is a very simple algebra problem, but suppose it's, the optimal is 100K context length, and you go to 200K context length. Does your MFU go down to like 50%? Like, does it have a humongous impact on MFU?
Yeah,
to be like slightly outside of context length, optimal range, Goldilocks zone?
That's right. So that is true as modeled here. There's a key point here that I'm modeling this context length as, or I'm modeling the memory fetch as linear in context length. That actually depends on model architecture. It is true for many of or all of the model architectures with dense attention. There's a sparse attention actually scales much better than that.
Got it. And is sparse attention what everybody uses in practice?
I'm pretty excited about sparse attention. It's hard to know what the labs are using. DeepSeek has published a sparse attention mechanism.
Okay, cool.
I'll just put a plug in that sparse attention, some of the DeepSeek papers that have published sparse attention end up putting a square root in this term. Okay, so far we've looked at the latency. It's kind of hard to read off cost from this. So if I think, what does cost mean? I'm going to run this inference, I'm going to use the GPU for a certain number of seconds, like 1 millisecond or 20 milliseconds or something like that. And I have to pay the rental time for that time. So like it's $2 an hour per GPU or something like that. So that's the cost of this inference. But how many tokens have I processed during that inference? That is the batch size. And so what we actually want to plot is going to be the cost versus batch size, which is like T over B versus batch size. This is the cost per token. So we have to imagine dividing each of these three curves by B, so multiplying by this reciprocal. And so what we end up with there is the compute curve is going to, it was linear, we divide by B, that makes it a constant here. This is T compute. The 𝐾𝐵 fetch was linear, now it becomes a constant as well. 𝐾𝐵 fetch. And then the weight fetch was constant, and now we've divided by B, and so it becomes this hyperbola. And so again, we're going to compute the max of the sum. So the sum of these two terms shifts the parabola up. Sum of the 𝐾𝐵 fetch and the weight fetch gives us a sort of a higher parabola that's like this. And then we're going to take the max with the compute here. So we end up with this being the overall shape that we care about. So again, so like we see some limiting behavior. The cost initially starts very high at batch size of 1. Actually, like it almost goes to infinity. It's because we've got so many weight fetches which are not amortized over a large batch size. But then as we increase the batch size, the weight fetches become amortized over so many different batch elements that their cost grows very small, and eventually the compute time ends up driving the cost.
Mm-hmm.
So there is a limiting like lower bound on cost, which is this line here.
Yeah. So Claude 𝐄𝐏𝐈𝐒𝐿 or 𝐄𝐏𝐿 or whatever would just live on this line, and it wouldn't help much because you're not able to amortize the 𝐾V values over a much bigger batch.
Yeah. They're unique per batch. The compute is also unique per batch. And so what is the minimum work you can do per batch after amortizing everything else away?
So this point where you are no longer memory bandwidth bound, what practically, how big a batch do you need to, like how big are the batches practically for frontier models?
You can just solve for that actually. And it's not even particularly sensitive to model architecture. So let's go ahead and do that. So what we're talking about is we're going to say when the memory time is equal to the compute time. That's what that question is. For now, I'm going to discard the, because we're focused on what the batch size is, and really there's a question of when the weights are amortized over the multiplies. I'm going to focus on comparing the weight fetch time to the weight multiply time. I'm going to disregard the KB fetch term, just to simplify the analysis, so we can get a kind of a clean answer out. So we're going to equate this portion with these two terms.
Yep.
So writing that out, we get n number of total parameters over memory bandwidth is equal to batch size times number of active parameters divided by the compute performance. So looking over here, everything on the top, these are model parameters. Everything on the bottom, these are hardware parameters. It turns out to be nice to rearrange them such that we have the hardware parameters on one side. So this is equivalent to flops over memory bandwidth being equal to batch size times number of active parameters divided by the number of total parameters. So this is a hardware parameter. Actually, this actually ends up being a dimensionless constant. If you look in terms of flops, what are the dimensions of this? This is multiplies per second. This is bytes per second, so that's not quite dimensionless. But what you do is you say like multiplies per second times, let's say I'm doing FP4. So I do like how many FP4 multiplies per second times the fact that each FP4 is half a byte. And so I can actually make this ending up being dimensionless. And this ends up being on most GPUs around 300. Somewhere around 300.
And sorry, has that ratio changed over time as we've gone from model generation to model generation where the flops keeps increasing?
So this is a hardware parameter. To what extent has the hardware changed? So from like A100 to H100 to B100, the flops has increased substantially. The memory bandwidth has also increased substantially, and it has remained reasonably stable. Cool. Yeah, and we can express this one as well. This is a sparsity parameter. Yeah. And I might even phrase it slightly different. Let's solve for batch size in total. We end up with, so we're just moving this back over to the other side. We end up with batch size needs to be bigger than approximately 300 times sparsity. So for example, if I have 100, like I activate in DeepSeek, I activate 32 out of 256 experts. So this would be like 8 for DeepSeek.
Got it, okay.
So this actually gives you a ballpark, which is like remarkably accurate to practice. Generally, people will go a little bit larger than this. They don't really want to be exactly at the balance point because real world efficiencies aren't as good as a roofline analysis would say. But like take this and maybe double it or triple it.
Okay, so basically it's like 2,000 to 3,000 tokens per batch. But then if you included the KB cache,
Yes.
the implication would be that the optimal batch size
should grow larger. So this is like, we solved for the equivalence between when compute time is equal to memory time. If I add in more memory bandwidth, like something that consumes more memory bandwidth, then I have less available for the weight loads, and so I need to grow the memory bandwidth more, and therefore the batch size more.
This seems incredibly small. Like a batch, this would be like less than one sequence, right?
Yeah. Okay. So I guess this is keep in mind that I'm talking about the number of tokens that I'm generating one more token for. So it's actually 2,000 unique sequences.
Got it. Okay, we're just talking about a single forward pass on these sequences. This is like do you think of it like the bash as the number of sequences rather than like?
That's right.
Okay, cool. Yeah. When I'm prepping for interviews, I often talk to experts in the field. So for Reiner, I chatted with two of Jane Street's engineers, Clark and Axel. Clark, who works on low latency trading systems, walked me through why Jane Street uses FPGAs to make sure that they have predictable nanosecond latencies.
You can just build these like giant grids of compute very easily that do exactly what you need, that touch 100 megabytes of SRAM and then get your response back in tens of nanoseconds very easily. And that's basically impossible on a CPU.
He then went on to explain why CPUs just wouldn't work for this kind of thing.
And so if you have a clock that's going every 3 nanoseconds, you actually have several bytes of information at a time to make your decision. That's as opposed to a CPU where you'll just collect up a whole packet, let's say a 1500 byte packet. And then you say, okay, this packet's ready. Here you go, CPU. You can start thinking about it now.
FPGAs allow you to react to the earliest part of the packet as it arrives, rather than having to wait for the full thing. We also talked about liquid cooling, network design, and many other things. If you're interested in this stuff, Jane Street is hiring. You can check out their open roles at janestreet.com/Dwarkesh. And if you want to watch the full prep conversation, we posted it there too. If you've got a frontier model and you are actually doing inference, surely they must have more than 2,000 concurrent users.
Yeah.
Is there any added latency from the fact that you need to have the whole batch fill up? Or is it, if you have a reasonable amount of users, it's so unlikely that it would not take you 100 milliseconds to fill up the next 2,000 slots?
Yeah. The way to think about this, I guess we think of it as like, when does the train depart as a model?
Yeah.
So let's say I've picked a batch size that I'm going to run at. Maybe I pick, this batch size.
Yeah.
And so and by the way, this intersection point is the same intersection point here. So I pick this batch size. I know that it's going to take, for example, maybe it's something like 20 milliseconds is a common place this ends up landing.
Mm-hmm.
What I'm going to produce is, so this is a timeline of what is running on the GPU. It's going to start a new batch every 20 milliseconds, regardless. And so each of this is 20, this is 40. Yes. You can think of this as a schedule for the train. A new train departs every 20 milliseconds.
Yep.
Any passengers who are ready board the train. If the train is full, then they wait to the next train. If the train is not full, the train's going to go anyway. And so in terms of what that means for queuing latency, it means that the worst case is that a request arrives just after the train departed. It has to wait for the next train, so that's up to 20 milliseconds, and then it has to wait for that train to complete. And so the worst case latency is 40 milliseconds.
So how is it 20 milliseconds derived?
Rule of thumb, but where it comes from is not fully explained yet, but so far we've focused on memory bandwidth and compute time. When we look at memory, the other consideration is that we want to use all of the memory capacity we have. And so generally we're going to use all of that memory capacity to store the weights or the KBs. And so we just want to read, like in the time of doing a forward pass, maybe we want to read all of the memory capacity into the chip. And so that is capacity divided by bandwidth. That tends to be 20 milliseconds on many different generations of HBM.
The units make sense. You would have a byte divided by bytes per second.
Yeah. So for example, on I think the Rubin generation, it is something like 288 gigabytes divided by 20 terabytes per second. And this looks like it comes out to about 15 milliseconds.
Yeah. Let me just make sure I understand what it's saying. I understand why the units can't, the sort of unit analysis.
Mm-hmm.
But what it's saying is, we can evacuate and replace the HBM in this amount of time, And so we don't want to be in a situation where the HBM is not big enough that we're not actually able to write everything we want to it or take everything out of it. Or we don't want to be in a situation where our ability to write back and forth is so big, or sorry, so small compared.
Yeah, there's sort of two scenarios. Why don't we pick a latency that is bigger than 15 milliseconds? And if I think what that means, it means I actually have time to read the HBM like twice.
Yep.
By the way, most of HBM access is reads, not writes. It's like almost all reads, because the weight matrices are read-only, and then almost all of the KV cache accesses are reads. So in, like, let's say I run 30 milliseconds, I can read all of HBM twice, but what's the point of that? Like, I don't want to read the weight matrices twice. I don't want to read the KVs twice.
Yeah, makes sense. Makes a ton of sense. Okay, so a couple of actually quick questions. One, if it is the case that the optimal batch size is something like 2,000, and that actually true, it's totally dependent on the sparsity, it's not dependent on the model size or anything.
I mean, sparsity shows up in model size, but beyond that, it only depends on sparsity, not on scale.
But that's a very interesting result. And that seems to imply that you can, one question is, how much of a push towards centralization is it that you would have these economies of scale from inference, from batching?
Yeah.
But it seems like it's not that big a deal. Like, I don't know, is 2,000 users at the same time a lot? It doesn't seem like a lot.
So we can do a bit of analysis on this, which would be actually, it's like, you can think of it in terms of number of users, but maybe a more productive way to think of it is in terms of number of tokens per second. So what does this batch size mean in terms of tokens per second of the system? So tokens per second is going to be equal to the batch size. We run a batch, many tokens, and then we do that every t. So every time intervals, which is, let's say, this thing is equal to the 15 milliseconds, 20 milliseconds number. So this ends up being batch size itself times about 60. So like 64 times b. And so this ends up being around 2,000 times 64. So like 128K tokens per second. So this is sort of in more digestible units. Like it's hard to reason about concurrent users, but what is the global traffic for a system? When you look at some of the announcements, sometimes the API providers will brag about how much traffic they have. The numbers that I've remembered from some announcements of Gemini last year were in the hundreds of millions of tokens per second worldwide. Yeah. So about 1,000, like this is 1,000th of that footprint.
Gemini. Yeah. But I mean, Gemini is big, so that's actually 1,000th of Gemini is a lot. To actually be like to be competitive at scale, you need to be able to serve at least 1,000th of Gemini.
Yeah,
that's interesting. Cool. Okay, so the more sparsity you have, the less compute you need. And it does seem that as batch sizes get bigger, compute ends up being the bottleneck, according to this analysis. So then the question is, how far can you take sparsity? That is to say, as the sparsity ratio increases, as you have fewer and fewer active parameters relative to total parameters, how much is performance of the model degrading? And is it degrading faster than you're saving compute by increasing the sparsity factor?
Yeah, so quality of the model, you mean, rather than speed of the model.
Yeah.
Yeah. So unfortunately, we're not able to answer that analytically. That is an empirical question of model quality. Best I can do is pull up a paper and answer that empirically. Yeah.
Okay. Should we pull up the paper now, or is it makes sense?
Yeah. So this paper, this is Unified Laws for Routed Language Models. It's a somewhat old paper by this stage, but one of the things that they did is looked at, if I keep increasing sparsity, what is the model quality impact? This answer is very sensitive to the actual choice of mixture of experts. Mixture of experts has been around for a really long time. I think it was even back in 2017. But the techniques have changed a lot. DeepSeek mixture of experts was a big change in how it worked. There have been older papers which are G-shard, switch transformer. So the actual empirical results are going to depend on all of that. But on one of the older techniques that is shown here, you can see if I hold constant the number of active parameters at a certain size, and then I increase the sparsity, which they call expert count here, the quality keeps increasing. And then if you imagine like drawing a horizontal line from 1.3b dense across, you end up seeing that, for example, in this case, the 64 expert 370 million activated parameters model is as good as a dense 1.3 billion model.
So in some sense, it's actually not amazing returns where you need to increase total parameters 100-fold to get the equivalent of 10x as many active parameters.
Yeah, I mean, actually, even more so. Yeah, it's a huge increase in parameter count for a modest increase in
Yeah. So in this case, actually, it's what is it? 4x?
64x for 4x.
So yeah. So while it is true, I guess, that you get this benefit of being able to economize on your compute time if you increase sparsity. Naively, it would seem like, oh, that's a trade-off worth making. But if you're decreasing this by 2x and then having this go up by 8x every time you double sparsity.
So is that good or bad, actually? Even from a memory point of view, keep in mind, you are doubling this portion of the memory fetches, which is amortized by batch. And so just keep running a larger batch size. From the point of view of the analysis we've done here, this is pure win. Keep doing it. Keep doing it until you run out of available users, basically.
Mm-hmm.
So there's actually this equivalence between if I want to go sparse, or if I have a lot of users, I can go to a much sparser model. So from that point of view, it's a reasonable trade-off. The other trade-off that shows up here is that it also consumes memory capacity, which we've only reasoned about memory bandwidth here, but it also consumes memory capacity.
So let me just make sure I understood. You're saying we want bigger, we want to spend less time computing, therefore we do more sparsity. To make that work, we need bigger batch sizes, which means we need more memory capacity.
So
to have more sparsity.
Yeah, so I mean, maybe this would be a good point to actually talk about how a mixture of experts layer is typically laid out on a rack of GPUs or something like that.
Yeah, makes sense. Yeah, where were we?
Sparse mixture of experts.
Yes.
Maybe how we lay that out on a GPU.
Yep.
So let's zoom in on the mixture of experts layer first and sort of draw what that looks like. So we typically we'll have some kind of a router layer, which is making the decision of where we route the experts, the tokens to. So we get tokens coming in here. They go through a router layer, and then we have a bunch of different experts. I'll draw a few more to line some up. And then the router will make a decision, which experts am I going to route to? And it'll be a small fraction of them, maybe 1 in 32. So maybe it'll make a decision to route to this one, maybe this one, and maybe this one. These experts, each expert itself is a normal MLP. It has an up projection and then a down projection with a nonlinearity in between. And then finally, we sort of do the inverse operation. So where we were broadcasting things out here, we're going to bring them back in and sum them up. So bringing them in like this. And then finally, we have our residual connections. The token is also passed through here, and it gets added to the result of the MOE layer. So this is a normal MOE layer. What I want to talk through is how this is mapped to a GPU rack, and what this means for communication. Because I think this will start to show some of the limits of how sparse we can go.
Yeah.
So the standard practice here, and it is the best solution, is to use expert parallelism. So that means different experts go on different GPUs. So if we take something like a DeepSeek model, they have 256 experts. Let's say we want to run that on a Blackwell rack. So there are 72 GPUs. We have a divisibility problem. This is not a power of 2. So we'll just simplify and say we're only going to use 64 of them. Just ignore the other 8. It's not a big deal. And so we have 4 experts per GPU. Very simple. For the sake of the diagram, I'll actually just say, let's say we have 2 experts per GPU. So we end up just putting, these are the GPU boundaries. Every pair of experts is on its own GPU. And then we can look at the communication cost. We had some experts stored, there's some tokens stored centrally here. They get routed to all of these experts. And so there's some communication cost paid here. There's the same communication cost paid on the output. And then the hope is that this does not become communication limited. Now, what is the traffic pattern here? The traffic pattern here is that any GPU, in fact, will be talking to any other GPU, depending on the decisions made by the model. So this is an all-to-all traffic pattern.
So when you say any GPU in the pretense,
Yeah.
the router is more than one GPU?
Yeah, the route. So I drew this as one router. In reality, you would actually have many copies of the router, and so you would have as many routers as GPUs, in fact,
As the incoming traffic.
Yeah. So these are 64 GPUs. These are 64 GPUs. It's actually the same GPUs. We just like draw them as separate because they're serving different purposes. So at this point, any GPU can be sending to any other GPU. So this all-to-all pattern of communication that shows up and how the Blackwell racks are configured is a perfect fit for the communication pattern that the MOE actually wants to do. However, if you think maybe I want to do, like maybe one rack is too slow and I want to do 2 racks, then I have this challenge that like maybe I've got some sort of rack boundary drawn outside here like this. And I no longer, in fact, have all-to-all communication between all the GPUs in 2 racks. And so the rack-to-rack communication ends up being a substantial bottleneck. So this sort of like the fundamental thing here is that one rack is actually bounds the size of an expert layer you can do. And so this has been part of what's been driving towards larger and larger interconnect domains.
Yeah. But before it may be worth you explaining what exactly a rack is, the differences in bandwidth between a rack and within a rack, and the all-to-all versus not all-to-all nature of communication within versus outside.
Yeah, and this is a place where it starts to be very different, in fact, between NVIDIA, for example, and Google, and then others, including us. So generally, a rack is it is a physical structure. It's a few meters tall, meter or 2 wide, depends on configuration, and it stores some number of GPUs or XPUs, which is typically about 64. What constrains it being a certain size is power delivery, weight, and cooling ability. It ends up being about this size in many cases because of these physical constraints. So then when I deploy a data center, like I've got, a data center may have thousands of these racks. So I've got one of these tall racks, it's got a bunch of GPUs in it, and so on. And then I put another rack next to it.
You make it sound so easy.
Yeah, right. I just like drop them in. In NVIDIA's case, the communication topology is actually they put the GPUs on the outside of the rack, and then they put these switches on the inside of the rack. So what this ends up being is that there's a set of switches in here. These are the NV switches. And then they run a bunch of cables. Every single GPU has cables going to the switches in the middle. So every GPU goes to the switches in the middle, and then the switches have connections to all the GPUs. So all of the GPUs can talk to all the other GPUs in just like 2 hops, going to the switch, going to the other GPU. Now, when I want to leave the rack, I end up going via a different path. The GPUs have also a much slower connectivity, which is typically about 8 times slower, which is, so the green that I drew here in GPU cases is the NVLink. More generally, it's called the scale-up network. This is the scale-up network. You will typically also have a scale-out network, which allows you to connect to like some data center switch. So data center switch. And then all of the GPUs will have some connectivity up to some data center switch somewhere. But this is about times, like this is the scale out. And it tends to be about 8 times slower in bandwidth. So the challenge, if you want to, for example, lay out a mixture of expert layer across 2 racks, is that half of the GPUs here are going to be wanting to talk to the GPUs here. And so like half of the, like just on average, like when I look at where the tokens on these GPUs want to go, half of the tokens want to go inside the rack. That's great. They can use the fast scale-up network. But half the tokens are going to want to leave the rack and go to the other rack, and that's not as good. They're going to need to use a much slower network. And so that becomes the bottleneck on the all-to-all pattern. A different choice would be, well, why don't I like have a big switch here and sort of like and connect everything to some big switching, like a much bigger switch that actually combines the two racks together. There are many ideas in this direction, but in general, it becomes the reason you have this sort of hierarchy of switches rather than one big switch is to manage the cabling congestion. You just need to run a large number of cables.
Sorry, is that question you just asked basically why isn't it a bigger scale up?
Yeah, exactly. Why not just like have like a million chips in scale up or 1,000 chips?
What has changed that has allowed NVIDIA to go from Hopper was 8, then Blackwell is 72, and now Rubin will be, is it 500 something?
Yeah, 500 and something, yeah.
What has allowed that to happen?
So from Hopper to Blackwell is mostly just the decision to switch from trays as the form factor. One of these is a tray to switching to racks as the form factor. That's a product decision. It's there wasn't a substantial technical barrier there. Switching from the like 64 to 500 or so, there's a bit of Jensen math there, but there is at least a genuine 4x increase, which is coming from a much more complicated and difficult rack design. And so that is actually like new physical design to run more cables.
And the cable complication is just the cost of figuring out which cable hops to which, or like which signal.
Yeah, I mean, let's sort of zoom in on this and look at the wire density. I'll draw this diagram just once more so we have a bit of a cleaner version to work with, and a larger version. Let's say I have some switches in the middle.
Yep.
And let's say initially I'm going to start with just 2 GPUs on each side, or two trays of GPUs on each side. And let's say maybe each tray wants to have 2 cables coming out of it. So I get some kind of, I physically run vertical cables that look like this running into the switches. Now if I want to double the number of GPUs in a rack, I need to run like literally twice the density of cables. So I need to run these as well.
Extremely naive question, but if you look at a physical data center, it seems like there's a lot of space within a rack. I don't know, just like the cables are like really big and...
Yeah, so there is space outside the rack. Inside the rack, like these racks are like, I mean, as they become more optimized, these racks are very tight. So there's connector density going from the tray into the rack and the rack's backplane, and then the backplane itself has a really high density.
Okay.
There are other physical constraints, including like bend radius of cables, like you don't want to snap them and so on.
Yeah. Okay, so it's literally the physical space to put a cable.
Yeah.
That's constraining it.
Yeah.
I had no idea. Interesting. That seems surprising that like. Yeah. The rack is so big, and just like we can't just stuff more cables in there.
Yeah, so I mean, rack design is not my expertise, but like when I talk to folks and what are the constraints they're up against, it's a combination of what are the big physical things you're optimizing for? Space, weight of the rack, like it's actually really heavy, and so like you need enough metal to not sag and fall, but then you add more metal and it's heavier, and then power and cooling, and so all of those are competing for like. Modern racks are pushing all of those to very extreme physical limits.
Deep work is by its nature quite aversive, so even things which seem like work, like Slack and email, can be easy ways to distract yourself. So I often wish that I could just turn the internet off. But if I'm prepping for an interview, even if I have the papers and books on hand, it's still super useful to be able to do a back and forth with an LLM so I can break down concepts and research follow-ups. Google's new Gemma 4 is the first open model that allows me to have this kind of fully disconnected focus machine. It's small enough to run on my laptop, but good enough to actually be useful. So to prep for this episode, I downloaded Reiner's scaling book and shut off the internet. I was able to have Gemma help me understand the material and answer my questions. If you want an LLM that you can run locally on your laptop or even your phone, you should check out Gemma 4.
when was GPT-4 released again? It was 2022 or 2023?
Three.
Okay.
Yeah.
And it was rumored to be over 1 trillion parameters. And it seems like only now, and within the last 6 months, have models been getting released that are significantly more parameters than the model released 3 years ago.
Yeah.
When supposedly there should have been this scaling in the meantime. Is the reason that we were just waiting for racks with enough memory to hold a 5 trillion parameter model along with its 𝐄𝐏 for enough users for a full for a lot of sequences, or RL if you're doing RL, kind of a similar consideration of actually holding the 𝐄𝐏 for all the batch of problems you're trying to solve. So if you look at like Hopper, you had 8 hoppers, and I think that's 640 gigabytes as of 2022.
Yeah.
With Blackwell finally, which was deployed 2020.
Very recently, maybe last year.
Last year?
Yeah.
You finally have a scale up with on the order of like 10, 20 terabytes, which is enough for like a 5T model plus 𝐾V cache.
Yeah. Deploying in larger scale up domains is a huge unlock. I mean, I've drawn here the sort of NVIDIA Blackwell deployment. The Google deployment has actually had very large scale up domains for a long time.
And that also explains why Gemini seemed to be ahead. Like was Gemini 2.5 was a successful, or it just seems like Gemini has that successful pre-train for longer than some of the other labs.
Not having been there at the time, I'm not sure how much is coming from like successfully deploying higher sparsity ratios, which could be. It could also be, I mean, there's a whole bunch of actual modeling things of like, specifically, how do you do the mixture of experts? We've seen the DeepSeek, like the DeepSeek mixture of expert has said, actually activate more experts, but finer grained experts was a big innovation.
Yeah.
I'm sure that there are many other innovations on the model architecture as well as on the training data. It's kind of hard to disentangle all of them, but what shows up in terms of the limits of what you can do, the active parameters, as we saw, is limited by the compute cost, and then the total parameters is limited by the scale-up size.
Yep. When you're operating within a single scale-up domain, is that a consideration specifically for either forward or backward, or specifically for prefill versus decode? Or is it preferred to always be within a scale-up, whatever kind of workload you have, whether you're doing a pre-training run or whether you're doing RL generation or whether you're doing inference for users?
Yeah, really interesting. So to answer that question, we're going to need to talk about the communication patterns so we've talked about the mixture of expert communication pattern. That is this all-to-all. This all-to-all. All-to-all. All-to-all very strongly favors full connectivity, which is what we've kind of just shown here, and it favors being within one rack. There are other kinds of parallelism besides expert parallelism, which we just showed here. In the literature is tensor parallelism. This is, with the trend towards smaller experts, this has become much less relevant, so we can ignore that. But the other two things that we have available are data parallelism and pipeline parallelism. And they are actually they can be a much better fit for using multiple racks. So let's focus on pipeline parallelism specifically. This is one layer of MOE. I'm going to have like 100 more layers up above. I could decide at this point, for example, to move to a different rack, change rack. Now, is that going to become a communication bottleneck? So we can actually just solve for when this becomes a communication bottleneck. But before we do that algebraically, let's just sort of visualize it out and sketch the path. So we're going to have a bunch. This is another MOE layer, and we're going to have another MOE layer here, and so on. So let's say I change rack here, and then some number of layers later, I change rack here as well. So our methodology that we're going to use to determine whether we have a communication bottleneck in this point where we change rack is we're going to compare this is the scale out bandwidth requirements to the scale up bandwidth requirements. So let's try this. And I mean, the hint is going to be that there's a lot more sends here. Like we're sending many things here, whereas we're only sending one thing here. And then we're also maybe doing it many times. So that's going to be the what makes the difference.
Can I try to guess?
Yeah.
Just out of curiosity to see if I'm actually understanding. It seems like you're sending like batch size into the rack.
In here?
Yeah.
Yes.
But the communication within a rack is sort of batch size times number of GPUs.
Yeah, so number of activated GPUs, right? So like I don't send to this GPU at all, right? So there's an explosion from 1 to like, it's 3 times larger here in this diagram.
Yeah.
The key thing is that I didn't even need to send to this GPU at all. And so that's a big saving.
I see, yeah.
Okay, so we're going to talk through sort of how much more, what is the slowdown of, to what extent is scale up a bottleneck over scale out. So we will directly jump to the ratio of the time spent on scale up, time on scale up, over the time spent on scale out. So this is the quantity we're talking about. And the first consideration is that the scale up is like, scale up is 8 times faster than scale out generally. And so at a baseline, if the bandwidths were the same, we would have this 1 over 8, which is coming from bandwidth. But then we have some amount of expansion in how much data we're sending. So if 1 token comes in here, then this 1 token gets routed to, in the DeepSeek case, it'll get routed to maybe 32 experts or 16 experts, gets routed to some number of experts. So this is the number of activated experts, And then it also, the same thing applies on multiple different layers. So maybe I'm going to run 2 layers. So there's also multiple times number of layers per stage.
And don't you need to multiply the whole thing by 2 for the
up
all
and
to
down?
all, yeah.
Yes. And there's a factor of 2. Thank you. So what we would like is for the scale up time to be greater than the scale out time, because like the scale up time is the more important and precious resource. And so we want this one, we would like this number to be greater than or equal to 1. And this really doesn't seem hard. Like there's just a factor of 8 that we need to overcome. So we need the product of these 3 things to be bigger than 8. Typically, we have a fairly large number of activated experts. It could be 8 by itself. And then we can increase the number of layers per stage a lot until we satisfy this.
I see.
So what this ends up looking like is that I can, in fact, have an entire pipeline of racks where one rack does 1 layer, and then I move on to the next rack, and I do another layer, and then I move on to the next rack. I can do another layer.
It's interesting to me that the best parallelism strategy in practice ends up being one which physically resembles the actual architecture. It's not some galaxy brain thing. It's like, oh, we have experts, we're going to put them on different GPUs. Oh, we have different layers, we're going to put them on different racks. Isn't that, I feel like that's interesting that the physical and...
The model architecture matches, like the coding matches the model architecture.
Yeah, exactly.
Yeah.
I mean, it could have been something wackier with tensor parallelism and whatever.
Yeah. So, I mean, I think a way to think of it is, the galaxy brain way to think of it is like, what are all the different dimensions in which a model is scaled up? And so there is, it is scaled up by layers, it is scaled up by the demodel dimension, it is scaled up by the DFF dimension, it is scaled up by the number of experts. Every single one of those numbers you can choose to cut along. And if those numbers are big enough, it eventually becomes profitable to cut along there.
Yeah.
And we have selected 2 of them. The other 2, in the way typical models are typically sized, are not profitable.
So there's a talk by Ilya where he says, today we know not to do pipeline parallelism. And Horace gave my friends and me, I hate that it sounds like a Dr. Seuss quote. But he gave us a lecture on these different kinds of parallelisms. And he said, the problem with pipeline parallelism is that it
other than the bubbles, it creates these architectural constraints.
Yes.
On like 𝐄𝐏𝐈𝐒, for example, has these residuals where attention attends to the
a fewer back or something.
Yeah, layers a few back, and so that it becomes hard to implement in this way.
Yeah. And I guess we didn't really fully articulate even what is the benefit that we're getting from pipelining.
Yeah.
And so these complexities are real. Pipelining is a massive hassle. But it does give you some benefits. And then you can then decide whether those benefits are worth the costs. The biggest benefit that shows up, so it has some benefits in inference, maybe bigger benefits in training. In inference, what are we saving on? Are we saving on memory time or compute time? Not really. We're just moving the memory time from one chip to another chip, or one rack to a different rack. There's no actual benefit in runtime. However, what we are saving on is that the memory capacity is the amount of memory used per rack. If we think that the memory in a rack is a bottleneck, then there's a constraint on how sparse we can go. Pipelining allows us to massively reduce that bottleneck.
I guess, but the opposite connotation to this, which actually, before this interview, I was chatting with Axel, who's a GPU performance engineer at Jane Street, and he was explaining, well, to do pipelining, you had to do micro batches rather than full batches. And if you do micro batches, then you're, by definition, not able to amortize loading the weights.
That's right.
Across all the users or all the sequences. And so the positive connotation on that is you don't have to use as much memory. The negative connotation is that you can't amortize loading the weights across all those users. And maybe it's worth explaining why you had to do micro batches, because you can't.
So we draw the pipeline bubble. Okay. So why do we do what is this micro batching that shows up in pipeline parallelism? So I'll focus on inference first. It's a slightly simpler problem. And I'm going to draw. So this is time, and then this is which rack we're on. And so the idea is that maybe I'll have like 4 racks. So I've got an inference that is going to like step through these 4 racks in some time like this. So great, this is inference number 0. It runs at a certain batch size, and it steps through all the pipeline stages like this. Now, if we were to say, well, we're going to run inference number 1 here, like this is clearly like a massive waste, right? Like, like 3/4 of the time, each of the racks is doing nothing. So we don't actually run inference 1 here. We run it as soon as we can, which is immediately after inference 0 finishes like this. And then we keep going. So if we hadn't filled this in, we would call this the pipeline bubble. When I've drawn it in this inference context where we're only going in a forwards pass, it's like obvious, like why would you do this stupid thing? But in a training context, it's maybe less obvious. But in the inference context, it's sort of really natural to make this change.
Oh, interesting. So this is sort of obvious, but the difference between micro batch and batch doesn't matter at all in inference, because you can just call whatever you want, whatever. It only matters in training because there is an optimal batch size.
Yes.
And before you do the backward step, you want to have accumulated, before you do a full backward step, you want to have accumulated all the sequences in that batch. And if you want to do pipeline and training, in order to avoid that bubble, you need to...
Should we draw the training diagram?
Let's do that.
Let's do that. So this is the inference diagram, and I'll call this 4 just so we don't have the wrong thing showing up there. So let's do the same thing for training now. We've got a forwards pass, but at some stage we're going to have to transition to a backwards pass. So we'll do some number of batches in the forwards pass. And then we're going to transition to the backwards pass for everyone all in one go. So the inference part is the same here, but then we do a hard stop at this point and then transition everyone to backwards pass. Similar numbering like this.
It may be worth clarifying. The reason there is that hard stop is because
you want to do a whole batch at once for the backward step.
Mhm.
And then there is an optimal size for how big that batch should be.
Yeah, I mean, smaller is always better, actually, is a way to put it. But it's like from a ML convergence rate perspective, smaller is always better because basically you're getting the freshest information from the gradient descent.
But total training time perspective.
Total training time perspective, it's worse. Like smaller is worse from a systems perspective, and so the optimum is the trade-off between those two. Yeah. So you pick a batch size, and you and then like for that batch size, you do some amount forwards and then some amount backwards.
Yep.
You asked why is there even a hard stop? The pipeline parallelism, because of this, the fact that you've got this idle time here, which is the bubble. There are so many techniques in the literature for how to lay this out differently and avoid that. There are more complicated schemes called like zero bubble or one forward, one backward, which sort of interleave the forwards and the backwards in complicated ways. But
you can mine Bitcoin in that bubble.
Right. More usefully, you can do the weight gradient step, but you can also mine Bitcoin. Yeah. So in inference, actually, the effect of pipelining on anything you care about, like batch size or latency, actually is neutral. It doesn't improve it, it doesn't make it worse. So if you look at the latency of this inference, running it if it were pipelined versus if it were all on one rack, if it were all on one rack, we would just like slide all of the boxes down and still put them in a row, and the latency would be the same. So pipelining is neither better nor worse for latency, but it does mean that you just use less memory per rack, like memory capacity, because now instead of needing the whole model, you only need a quarter of the model in
Makes a
HBM.
ton of sense. So basically, no brainer to use pipelining during inference, but there's this harder trade-off during training.
So even in inference, in fact, it is not used a ton. It reduces your memory capacity requirements. There's actually a huge surplus. Like I think you're saying that a rack of Blackwell has many terabytes, maybe tens of terabytes of that's much bigger than like a trillion parameter model. A trillion parameter model only needs 1 terabyte. And so it already fits, in fact. And so there's not a huge benefit from pipelining because you're reducing a number that's already pretty small. But it does say that theoretically, maybe you had too much memory there. And maybe you could have done a different, build a different hardware that has less memory, in fact. If you were designing your hardware, and you said, I actually didn't need that much memory because I don't need the weights to fit in one rack. I can fit the weights in 8 racks. Then I could have maybe built a hardware that didn't have so much HBM per GPU.
Last week, Horace was kind enough to give me and my friends a great lecture on large-scale pre-training systems. And there were some concepts that I wanted to animate for a write-up on my blog, like how weights shard and gradients flow depending on the parallelism that you're using. So I gave Cursor my lecture notes and a sketch that I'd made during the lecture, and I asked it to visualize a specific hierarchical collective that Horace had explained. The first version was already pretty good, and then I was able to use design mode to select and tweak any specific components from there. I was able to do all of this without a clear end state in mind. Cursor's Composer 2 Fast model was quick enough that I was able to iterate almost instantaneously. I could try an idea, test the results in the built-in browser, and immediately make any changes. I went through 10 different versions in under 20 minutes. If you want to check out this animation, I published it along with the lecture notes in a blog post. The link is in the description. And if you want to try out this kind of iterative design flow for yourself, go to cursor.com/Loarcash to get started.
So macro question. Everybody's talking about the memory wall right now. Memory's getting super expensive. There's not enough memory. Smartphone volume will go down 30% because there's not enough memory. Hyperscalers are spending, but this is shocking. Dylan said they're spending 50% of their CapEx this year
On memory?
on memory.
But that's believable. Yeah.
But what is hyperscaler CapEx? That's like high hundreds of billions, maybe a trillion. And they're spending half of that on memory. Okay, so that is a huge constraint. That's why we're not going to get new laptops and phones this year. But at the same time, we have too much memory. Like people are willing to put too much memory into these systems.
Right. So this is
like why is Jensen shoving all this memory into these racks if you don't need it?
Yeah. So we've in the equations we had here before we raised them, we were doing memory time, so memory bandwidth and compute bandwidth. Let's now start looking at memory capacity.
Yeah.
So we'll start off with just like memory capacity without even thinking about parallelism scheme. And so the capacity of memory or the demand on memory is the number of total parameters plus, so this is what we need to fit the weights in some system that we are using. And then we need to fit the KVs as well. So KVs go as batch size times the length of the context times the bytes per token. Okay, so what I was arguing about in this context, and the case I was making for pipelining, is that there are some techniques that allow us to solve this. Are there techniques that allow us to solve this? So let's consider. So we're going to run this on some number of GPUs, and we're going to say we're going to have one extent, which is E is going to be the expert parallelism. So how many, when we had this sharding of expert layer across many GPUs, how much of that, to what extent do we do that? How many GPUs? So we're going to say that this is, for example, 64. And then P is going to be the extent of pipelining. And so this is the number of racks, which who knows, maybe we'll pick 4 or something like that. What we want to calculate, so this is like the total memory requirement across the system. But now I'm going to calculate a memory requirement per GPU. So per GPU memory requirement, we're going to have, I guess I'll use a lowercase c mem. And well, obviously we just take all of these numbers and divide it by E and P, really easy. So it's this n total plus the batch times length of context times bytes per token. All of this is divided by E times P. Okay, so this is like, why is this correct to divide it this way? Well, we're saying we knew that the parameters were perfectly divided amongst all the GPUs in a rack. The layers are perfectly divided amongst the different racks. So that works here. And somehow we're going to arrange, I'll hand wave exactly how, somehow we can arrange the same perfect sharding of the contexts across GPUs in a rack and then based on layer across racks.
And sorry, 4 is the number of racks.
Yeah, for example.
Yeah.
So this is the place where we actually need to go back and analyze this batch size B. And you were making this comment that there's micro batching versus global batching. So let's come back to this pipelining diagram here. We've got one batch going forward here. And then as I drew it, it kind of just like disappeared. That's not really correct. If you think about how decode is working, I have a bunch of tokens that I have generated already. I do one forwards pass where I generate a new token. And then I push, like, then I write that to my KV cache. Yeah. And then I do another forwards pass that generates the next token. So I'm actually going to be running this batch 0 in a loop. So in fact, I go forwards. Once I finish, I can start the next iteration of the loop up here.
Yeah.
So we'll just fill this in. We'll have the
nice.
Yes. Yeah. So we've got the 2, 3, 2, 3, and 2, 3. So let's split this batch. This batch will be the global batch size. So B is going to be the number of micro batches times the batch of, like, the batch size per micro batch. So how many micro batches do we need? So the number of micro batches in this diagram is 4, 0, 1, 2, 3. And then the batch size per, like the micro batch size, this is still this like 2000-ish number. This is the one that is like, this is the like 2000 times sparsity. Sorry, no, this is the 300 times sparsity. 300 times sparsity.
This is the how big the train that takes up every 20 milliseconds is.
Right. Yes. This is going to be the 20 milliseconds train. So the global batch size is the number of microbatches times the local batch size. Local batch size is set by this hardware parameter. The number of microbatches, well, the number of microbatches is as small as possible such that we can like wrap around and not leave any idle time when we wrap around. So if we had fewer, we would have this idle time when we wrap around. And so you can sort of just visually see that it is equal to the number of pipeline stages. I mean, sort of proof by visual here, like it is 4 and it's 4 this way as well. But like you can sort of look and see that it goes along here and then it wraps around number of pipeline stages.
Yeah, and sorry, a very basic question. Yeah. This is what is actually done?
Mm-hmm.
Okay, like as in a frontier model today, we'll actually have, during inference, have pipeline?
For sure, during massive scale training, this is done. It can be done for inference. I'm actually going to make the case for why it is less attractive. It is useful for weights, but not so useful for KVs.
Okay.
Yeah. The big challenge is, so let's fill this in. The microbatch size here ends up being equal to the number of pipeline stages.
Yep.
When we go back and substitute this all of that into here, we get a number of pipeline stages times this little b showing up in here. And then when we factor this out, I'm going to split this into like this plus into two terms. We get the full division by E times P over here. We still have division by E times P over here, but the P's cancel, this P and this P. They cancel. And so what we find, if you increase the number of pipeline stages, the memory footprint for the number of weights keeps going down and down and down.
Of course. But
the memory footprint for the number of activations stays constant. So it doesn't actually work. Like most of your memory ends up like, once you do enough pipelining, and it's really not much, like even 2 is often enough, this term becomes very small. This becomes the dominant term.
Yeah.
The KV cache becomes the dominant term.
Yeah. I know this is wrong. I'm just trying to think out why my train of logic here is wrong. If you have many different, if you're pipelining through many different stages, the KV values are not shared between layers. So why would it not help to be pipelining across multiple layers? Because then you don't have to store.
Yeah, you only need to store like 1 layer rather than 2 layers of KVs, right?
Yeah.
So it helps from that perspective. You're right. What's competing with that, though, is that you need to be keeping all of the racks usefully busy at a time. And so the number of sequences that are in flight simultaneously has gone up.
Yeah, makes sense.
So those exactly cancel, and you end up not getting a saving per GPU.
Right. This is going back fundamentally to the point of you're not able to amortize across KV caches.
Yeah, well, so first you can amortize KV caches across batch size.
Yeah.
And now we're saying you also can't shard it across pipeline stages. It sucks from both of those points of view.
Yeah. Interesting. Okay, so then what is done during inference?
So, I mean, the DeepSeek paper reports what they do, which is like, they just do a lot of expert parallelism. You should, in effect, you should increase your expert parallelism up to your scale-up domain size, and then do very little pipelining. Maybe none at all, maybe 2, just enough to make the weight storage not too big of an issue. Those are the only 2 parallelisms that really make sense. In the past, there was tensor parallelism, which was cutting up within an expert, but the experts are so small now that is not a profitable optimization.
So this goes back to the question, does that mean that frontier labs, when they're doing inference, are just basically within a single scale-up?
Yes. Yeah, I mean, you can look at how it depends on model size. Like, you could have a very large model, like one that exceeds the memory of a rack. And there you should be doing a bit of pipelining. Maybe it's extremely sparse, for example, and that would be a reason to do it.
So I guess this goes back to the question about, or this goes back to the promise at the beginning of the lecture, which was, this will actually tell you about AI progress as well. To the extent it is the case that model size scaling has been slow until recently, because, let me make sure I understand the claim. The claim would not be, you could have trained across more racks. It was just that it would not have made sense before. Like, we didn't have the ability to do inference for a bigger model easily.
Actually, I make the claim, so pipelining doesn't help with context length. it totally helps with model size. And so because of the ability to do pipelining, at least a rack should not be a constraint on your ability to fit the model parameters. I guess the other consideration you're asking, like, why hasn't it scaled up more and why did bigger scale-up domains help?
Yeah.
So we talked through one aspect of that, which is we kind of said it's not because of memory capacity. We have a solution to the memory capacity, at least with respect to model size, not with respect to KV cache size, but at least with respect to model size, we have a solution to memory capacity. The other issue that shows up is latency.
I was just about to ask. So what is going from rack to rack, what is the latency cost per hop?
This is very much dependent on the hardware.
Yeah.
I can't say with a lot of authority. I think it's probably on the order of a few milliseconds, but it could be off by an order of magnitude there.
Is 4 a realistic number of how many pipelining stages you might have?
Yeah.
Okay, so that's not that much.
It's not on a small number of pipelining stages. This is not a huge latency impact.
Wait, I guess it's 10 milliseconds per token.
That's right. Yeah.
2 times 4-ish. Or I don't know how many you said, but
10
milliseconds per token is actually a lot.
Yeah, if it goes from 20 to 30, right, or something like that. Yeah. This is so, like, just to chart the path that it goes through. Here you're going from your GPU or TPU or whatever to a network card, which then goes to like a top of rack switch, and then hops over to the other rack and does the same thing in reverse. So you sort of have to sum up the latencies of these different things.
So this is the same thing as the DC data switch?
The data, it may in fact go up to a data center switch and back. Depends on deployment configuration.
Got it, yeah. And because it's decode and sequential, it's also not they stack up across the stages.
Yes, they do.
You can't do them at the same time.
That's right. Yeah.
Okay, so I guess this brings us back to the question then. Is the size of the scale up at all relevant to why AI model sizes or whatever have been what they have been over the last few years, whether through training or through inference?
Yeah. So I mean, we talked about latency of the hop of this hop. There is also just the same TMEM latency, the memory time latency, is actually substantially, like massively improved by larger scale up domains. So I'll recall TMEM down here. TMEM for the weights, TMEM of weights, this was equal to the number of total parameters divided by the memory bandwidth. Which memory bandwidth are we talking about here? Is it just one GPU, or it's in fact, it is the number of GPUs that I can use in parallel to load these weights. So I can't use different pipeline stages in parallel because they're not running at the same time, but I can use all the GPUs in my scale-up domain in parallel to load the weights.
Yeah.
And so this is actually extremely effective. Basically, I end up with a term here. This memory bandwidth term itself is equal to like scale-up size
times the memory bandwidth per GPU.
Yeah, times GPU bandwidth. And so this term doesn't increase a lot. It maybe increases 1.5 or 2x per generation, but this one increased by like a factor of 8 from Hubbard.
So the reason the bigger scale up matter is not the memory capacity of the whole scale up, but really the memory bandwidth.
Yeah. Pipelining totally solves the capacity problem, but scale up size helps solve the bandwidth problem.
And the bandwidth problem helps you do longer context lengths, which is more and more relevant as these models get more agentic.
Yeah, it lets you just run the model at lower latency as a first thing. Like if I just do a very sparse model and it's on like a little like H100 box, the latency will be really high.
Yeah. Okay, a super tangential question. There's Chinchilla scaling, which tells you how big should a model be relative to the amount of data you're going to train it on. But now, obviously, you're not just trying to optimize for the highest quality model you could get with training compute. You want the best results a user can get with a mixture of training and inference compute.
Mm-hmm.
So then there's a question of how much should you overtrain a model such that that compute amortized over training and inference is minimized to get a certain performance. But now with RL inference, there's another consideration, which is you're going to do some amount of pre-training.
Yeah.
That pre-training will be used both for RL generation and then for inference for the final user. And by overtraining here, I mean, while it would have been more efficient just from a training computer perspective to have a bigger model that you train for less time because it can learn faster. Maybe you get a smaller model, you spend more compute training it than you otherwise would have, but now it's cheaper to give it to users. Like basically, okay, maybe but let me make the question more concrete. How much more than Chinchilla-optimal are models overtrained?
Yeah.
And has that changed as a result of RL generation?
This is a place where we have to do a bit of guesswork because like the updated scaling laws and the model traffics are not reported, and so we have to guess there. But one way to look at it, let me first just make a sort of a general heuristic claim. If I have some like cost and I've got a total cost, which is a sum of like cost A and cost B. Like maybe this is the training cost and this is the inference cost.
Yep.
And so I want to minimize this sum. For many curves that tend up being the case, the minimum tends to be where the costs are equalized. That's something of a heuristic claim, but like there are many examples where it's true, like where one is 1 over x and the other one is x, for example. They tend to be minimized at the point where they equal each other. It's also true for like e to the x and like e to the minus x and all kinds of other things. Like so, basically, I've got some curve that's going down, some other curve that's going up, and they tend to be minimized at this equal point. Heuristically, I will conjecture that that is true for the setup you described as well. Like actually showing that would be true would require looking at the scaling laws and like fitting these like weird exponents. But things that do follow power laws tend to have this property. So I'll just make that claim and move on. So we're going to say that the cost of training plus the cost of inference, we want to equalize these. We'll do pre-training only first because it's a little, well, actually, we can do all of it in general. So actually, we'll cost it as cost of pre-training. So number of active params times the data on pre-training. So that's the cost of pre-training. There's a factor of 6 out here, which is the number of flops. This is the famous 6ND formula. And then in RL, we have approximately the same thing. We've got like same number of active parameters, but now it's the amount of data is the RL data. There's this extra like efficiency multiplier, which is, or inefficiency, like the inefficiency.
Which is the fact that you're not training on all your rollouts.
Well, yeah, there's that. And then the other, perhaps even bigger inefficiency is that this involves a substantial amount of decode, and often decode runs at less MFU than training.
Okay, so if you're doing a backward pass on every single generation in RL, it would be 6 ND.
Yeah, so this could be a smaller number, right? Like this could be somewhere, so...
they would at least be 2.
Yeah, that's somewhere in the range of 2 to 6. Yeah, so we'll just we'll say somewhere into the range of 2 to 6 and leave it at that.
Yeah.
And then we can add in the inference cost. The inference cost is 2, number of active times the data in inference.
And sorry, I think the way I said it was super garbled. So just for the audience, maybe forward plus backwards per parameter is 6. Forward alone is 2. That's why RL, where you're definitely going to generate all the trajectories, but you might or might not train on all the trajectories, is 2 to 6.
Yes. Yeah. Thank you. And then inference is just 2.
Yeah.
So we're going to solve for essentially maybe equality of all 3 of these terms. That is ballpark where people are going to be. Like labs have more information on what is productive in doing more RL, for example, than versus doing more pre-training. I don't have that information, but I think a good ballpark is 30-30, like 33% split between each of them.
Actually, I'm not sure I understand the intuition for that. Another naive model could have been that RL plus pre-training would be 50%, and inference would be 50%.
Yeah, that's also a valid answer as well. Because this is heuristic, I can't really argue for one versus the other. They don't differ by that much. Like 33 versus 25 is only a small factor off. So let's pick one of them. All equal seems simple enough. And so we're just going to solve for equality of them. It's pretty straightforward. We can immediately see that the number of activated parameters totally disappears. And so let's factor that out. And we're going to just say that data in pre-training. I decided to do it your way. It's a little bit nicer, actually. So data in pre-training plus this. Oh, I didn't have the inefficiency over here either. Inefficiency. Data in pre-training plus some multiple of like alpha times the data in RL is just going to be end up equal to the some beta times the data in inference. And then let's just like roughly size the alpha. This alpha, it's going to be this is like it's maybe somewhere in the range of 2 to 6. 2 to 6 over 6 from this term compared to this term. And then we've got an inefficiency term, which I would say is maybe in the range of like 30% or something like that. So this alpha is going to be something like 1 on 10, 1 over 10, let's say. And this beta here is actually the same. It's a third. It's 1/3 times 30%. So it's also equals 1 in 10, something like that.
If both of them are 1 in 10, that kind of implies that there's never a backward pass on RL.
Yeah, okay. We can make this like 2 in 10. Make it a bit bigger. Yeah. So yeah, like just write it out once more. Like this is 2 over 10. This is 1 over 10. So the number of inference tokens you have, and this is just a function of like, I've got hundreds of millions of tokens per second, times my model is deployed for, I don't know, 2 months before I shift to the next version. That should determine the number of tokens in RL and pre-training. And then I guess we didn't do the equivalence between pre-training and RL, so we'll do that here. Data in pre-training should be equal to like 2 over 10 times data in RL for them to be cost equivalent. So, sorry, this 1 over, I got it backwards. Like we pay more cost when it's inefficient. So this needs to be 1 over. So this, tracing this back forward,
5x, yeah.
This thing ends up actually being, as written here, it's like, yeah, so this is like 1.5 and this is 1.
Billions of dollars worth of compute just flowed the other direction.
Yeah, right. I think like if you do it with a spreadsheet and like actually model it out, you might notice when the money's going down the drain. Yeah. Yeah, so I think all of these end up being close in as modeled here. This 30% may have been a little bit too generous. So let's say something like 1.5 here and leave this as a 1 here. So I think at this point, you can almost read it off. Like the number of inference tokens should be about the same as the number of pre-training tokens, should be about the same as the number of RL tokens within like factors that we're not able to reason about.
But then, so it looks, sorry, I'm making a basic algebra mistake. It seems like there should be less RL tokens than pre-training tokens.
Yeah, that's in general right, because RL is less efficient in terms of machine time. And so if you're trying to equalize the RL and pre-training time, then you should have fewer tokens in order to have the same wall time.
This is all quite interesting that I never thought about it in terms of how much equalizing in terms of data.
I mean, I think starting with equalizing in cost is right, but depending on how you model the cost, this comes close to equalizing in data.
That if every single user who uses, basically for GPT to be trained optimally, every single user who uses GPT-5, the total amount of tokens that they stream should equal the total amount that have gone into pre-training.
Yeah.
And the total amount of tokens that have gone into pre-training is the sum of all human knowledge. So like each model should generate the sum of human knowledge on the output that it gets on the input.
Yeah. So, I mean, which way are people going to err? Like, if you think that people's power of prediction is not perfect, and also you run the risk that your that you make a model that is not a frontier model, and then you just throw it away,
Yeah.
then like that kind of changes the cost trade-off, because there's some like probability that applies to the inference, and you should derate the inference tokens by some amount.
Right. And then can we back out how much more compute than Chinchilla-optimal for a given sized model?
So I think we just have to make some real world assumptions here in order to do that. So, so the inference tokens, we should totally be able to count, right? Like, so let's say a few 100 million, I don't know, maybe it's like 500 million tokens a second now. I don't really know. 500 million tokens a second times a model is deployed for 2 months before it becomes obsolete. I don't really know. I can't do this in my head. Can you type it into a computer?
2.6 times 10 to the 15th.
Okay, 2.6 times 10 to the 15th. Okay. This number is probably too large. This because this is going to be multiple models in a family. So let's make it like 5 times smaller or 10 times smaller or something like that. Okay, so we're estimating maybe 50 million tokens per second per specific model. The model is live for 2 months, and so this comes out to around 200 trillion tokens. And then we want to compare that to active parameters on a frontier model. I don't actually know the latest rumors, but some... Do you know?
Somebody told me 150 trillion.
Active params?
Sorry. I meant tokens.
Trained on 150 trillion tokens. Interesting.
Which is similar.
Yeah, that's actually similar. So so data on pre-training.
This is not well cited, but
you want me to not remove
no,
this?
It's fine. It's fine.
Okay. And I think often active params, number of active params could be in the range of like 100 billion, something like that.
Yeah.
Maybe a bit larger. So I'm assuming active params of about 100 billion, and so multiply by 20 to get the Chinchilla token count. So Chinchilla would be around 2 trillion. And we see like we're about 100 times larger than that.
Actually, what does de-Chinchilla actually mean?
Like the token count for pre-training for that the Chinchilla scaling law would recommend, I guess.
Oh, I see. So how much is it overtrained? Got it.
So yeah, like the ratio of this 200 trillion or 100 trillion parameters over the Chinchilla-optimal of 2 trillion. That's the amount it's overtrained, which is like a factor of 100 overtrained, perhaps.
100. That's whatever. Okay, so if you consider this right here, to the extent this is in the right ballpark, just by thinking about, okay, you kind of want everything to be equal in terms of compute. Here's if that OpenAI also realizes that, and they're serving a certain amount of tokens per second, that tells you how much data went into the pre-training of GPT-5. Even if it's like 50% off or something, that is sort of wild that you can sort of first principles these kinds of numbers.
This is also, I mean, this is why you should just like approximate everywhere, because like there's so big error bars on this. But yeah, no, it's kind of like empowering to just like set A equal to B and figure it out.
Yeah, that's super cool. Okay, so in the spirit of trying to deduce things, we can publicly look up the prices of the APIs of these models, and maybe you can learn something from that. So first, with longer context, Gemini 3.1 is 50% more expensive if you go over 200K tokens than if you're below 200K tokens. I mean, at a high level, I understand why that might be, but why specifically 50%?
Yeah. So I mean, why specifically 50%? Let's sort of so the high level, even in the first place, is there is some amount of increasing cost with context length.
Yeah.
And we can bring that back up. That was the memory time versus the compute time. So okay, so we've put up these same equations from before of the time for memory fetches, which is the weights and the KB cache, and then the time for the compute, which is just the matrix multiplications for the weights. I will also draw the cost curve. but this time I'll do it as a function of context length instead of as a function of batch size. So this is time over, just time. And so this is the cost curve as a function of context length. We'll draw the compute. The cost of the compute is actually constant as a function of context length. There's no dependence here on context length. In reality, there is some dependence, but it is very mild dependence, so we'll ignore it. So this is the time for the compute. This one. And then we'll also draw the dependence of the memory fetch on context length. And this starts at a large number for the weights and then grows gradually with the context length. So maybe here, and then grow gradually with context length. And so you take the maximum and you see there is this inflection point here. So this is the costs that, for example, Gemini might be paying. And then you think, how might you put a pricing structure on top of that? You would like to ensure that no matter what the context length is, you are still profitable. So
interesting.
And so we've got a 2-tier pricing structure. Maybe we've got something that looks like this up to some max context length.
Fascinating.
So I think it says something about, given that the bump is at 200K, it probably means that this is somewhat aligned with this crossover point, maybe not exactly aligned with.
Fascinating.
So we can actually probably even complete that calculation just to see where it lands out. We can solve for the number of bytes per token if we sort of make some assumptions about the number of active parameters. So solving for the number of bytes per token, we're going to assume like the point where we equalize the time of memory and the time of compute is at, let's say, 200K tokens. So we equalize these two. We're also going to just assume that the batch size is large enough that the memory time spent on weights is negligible. So we'll forget about this and we'll focus on the actual memory time spent on KB cache. So that ends up saying copying this time over batch times len context times bytes per token over mem bandwidth is going to be equal to number of activated params over flops. And then we're going to solve for bytes per token. Batch size was missing here. Shows up here, and then it cancels out by the time we get to here. And I dropped the len context.
Yeah.
So we can plug in numbers. This number, this is the reciprocal of the number that we saw before. This is like 1 over 300, which is reasonably stable across many different hardware platforms. We conjecturally said that maybe number of activated tokens is like 100 billion. And length of the context we said was 200K. Something is wrong here. The length of the context should be on the denominator, not the numerator.
1667, like about one kilo, almost 2 kilobyte.
That is plausible actually. So you said around 2 kilobytes. So let's just do a sanity check for this, for what this could be. There are 2 mechanisms that people do attention with a small number of bytes per token. One is dense attention with a lot of reuse across layers. So Character AI has a blog post talking about that, alternating long and short context. And like in the Character AI kind of model, which also showed up in the Gemma models, the global context, which is really what we're talking about here, global context, was shared across all the layers. And so to get this 2 kilobytes, you could get that, for example, as a D head of 128, is typical. And then like the number of bytes is typically number of attention layers times 2 times d head times number of q heads. So this is the number of unique contexts per layer. Do you share the context across many layers, or do you use it only once? So in character AI-like models, this number is 1. We said this is 128. And this is a choice which typically ranges from 1, sorry, this is 𝐄𝐕 heads, I meant.
So the difference between a head and a 𝐄𝐕 head is that
the 𝐄𝐕 heads are the heads that are stored in memory, like store the contents of the previous tokens. The Q heads are the retrieval heads. They're only used temporarily, and they're used by the attending token. So in this autoregressive context, I've got 𝐄𝐕 heads associated with all of the context, and then Q heads associated with this new token here.
But this head, the 128.
Oh, this is this number is actually the same for. Oh, so this d head is the dimension of the vector.
Yeah.
And number of 𝐄𝐕 heads is typically in the range of 1 to 8.
Yep.
So, like, it is totally plausible to get this by, for example, having 8 𝐄𝐕 heads and a d head of 128. That gives you exactly this number.
Yep.
Or you could have like fewer 𝐄𝐕 heads but more layers. Yeah. So this is one way to get there via dense attention. There's also a way to get there via sparse attention, where you increase all of these numbers, but then you have like a 1 over sparsity term. So yeah, I mean, I think this number is plausible if maybe a little bit small.
It's funny that they would leak so much information through their API pricing.
I mean, you are incentivized to price close to your costs because otherwise someone could scoop you.
Maybe we can learn something about the difference in input versus output prices.
Yeah.
And what that tells us about decode versus prefill in these models. And I think last I checked, it's like 50% more expensive or something like that. Or
I don't remember. What I've seen in the past is like 3 or 5 times more expensive.
Okay, actually, that makes more sense.
Yeah.
So let's say it's 5 more times more expensive. Okay. This is the compute to process the next token in decode. Suppose you're doing prefill, where you're not just processing the most recent token, you're processing all the tokens in parallel. So I want to say that it would be this times len prefill.
Sure. Or length of the pass in general. Yeah. If we say like, if we can think of decode as being a pass with 1 and then prefill being a pass with many.
Oh, okay. Yeah. So maybe like prefix.
Sure.
Whatever. Okay, memory. So you're not storing the 𝐄𝐕 cache if you're for the tokens that are the prefill tokens.
I think maybe it's sort of let's draw actually how prefill shows up here. If I may clarify, so we do a bit of decode like this.
Yeah.
We may actually come back and do more prefill. Like if you think this is a chat session, the user says something, the AI generates a response, and then the user says something else, and we prefill this. So like maybe this is the more common, like this is the general case rather than this.
And in fact, this is like you read a file or something.
Read a file, or just like the AI is responding to user input or tool call or anything that's not AI generated.
Yep. Okay. Okay. So suppose we're here. So you will need to load. Basically, you will have calculated all of this previously.
Mm-hmm.
So just the 𝐄𝐕 of everything that came before. But what is the memory cost of this? Well, memory bandwidth cost of this. If you're doing flash attention, it would.
Yeah, it's basically temporary. It doesn't even go to main memory. Just ignore it.
Okay, so then it would just be everything that came before. So is it not just that then?
Yeah, there's actually no adjustment at all to the memory time.
Great. Oh, so it's a very trivial change to accommodate. So this term is making it 5x more expensive. Now, why would that be? Or what does that tell us about, what are we trying to learn here? What does that actually tell us? What variable does it help us clamp? Well, the compute has presumably gotten the only thing that could have changed is the compute is 5x more expensive as a result.
So yeah, this is the time for one pass, but actually the amount of tokens is that much larger. So I guess we want the cost per token, in fact, or the time per token.
Sorry, I'm not sure I understood. This is for processing the next token and prefix.
Well, actually, for processing the entire batch. So in this, like at this cost, we have processed this many tokens, like len a prefill.
Yeah.
Well, I guess like of the pass. Like, yeah. Not this prefix, but it's this cost.
Okay, let's just change it to pass. So this is 5x more expensive. Input is 5x more expensive.
No, output is more expensive.
Output is 5x more expensive.
So the result we want to work towards is that prefill is compute limited and decode is memory bandwidth limited.
Why don't we do this? Why don't we just chart it with like len pass on the x-axis?
Yep. Yeah.
And t on the y-axis.
We want the cost per token, so it'll be t over some stuff. T over length of the pass.
Mm-hmm.
Yeah, that'll be right.
Okay, so okay. It gets me thinking confused about this. Len pass is it seems like this should be higher when you're doing prefill.
Prefill has a bigger length pass. Yeah.
Right. But then why is it cheaper?
Why is it cost higher? Yeah. So, I mean, it's this division by length pass that actually makes it all. So
okay, yeah.
This is going to divide out. This is going to divide out, but then we're going to get all of this is going to divide by length of pass, and it's going to make the memory cost cheaper.
Okay, yeah. Let me think about this then. Okay, so let's do one line for. Basically, we'll have 4 different lines. Let's do prefill first, and so actually let's do decode first.
So actually, I mean, length of the pass when it's 1, that is decode. When it is bigger, that is prefill.
Right. Okay. I see. That makes sense. Okay, getting back to it. So T compute, if you have basically just this divided by length pass, is just this amount. So this actually does not vary based on T. So it'll just be some flat value like this. And this is T compute. And then this is like,
that's decode.
Decode, right. Now tmem, if you have this whole thing divided by length pass, well, it doesn't really matter what's up there. It'll just be something that looks like this.
Right. Yeah.
Let's say this is T mem. This is decode again. So as the length of the prefix goes up, or pass, your memory bandwidth time declines. And that means that to the extent that you were bottlenecked on memory bandwidth before, you can avoid being bottlenecked on memory bandwidth. The fact that they are charging 5x less for prefill than decode does suggest that they are bottlenecked on memory bandwidth to quite a degree, such that for them at least, because T is equivalent to cost, right? It's the cost of renting a compute. This is actually like, this would be at 1 and this would be at 5.
That's right. Yeah.
So it is in fact tremendously memory bandwidth bottleneck. The real graph looks something like, like that.
Yeah, I mean, it still crosses, but
yeah, exactly. So yeah, let me do it this way.
Yeah, that's right.
And then this is the gap on decode between the memory and the compute time.
Yeah.
Okay, interesting. Another interesting one would be why cache hits are so much cheaper.
Yeah, okay.
So I think if I remember correctly, cache hits are like 10x. It's more expensive to write to cache according to the pricing on all these models. But if you do hit a cache, it's 10x cheaper. So what is going on with, presumably this is the cost of keeping something in HBM rather than just evacuating it. But if you do keep it in HBM, then it's cheaper to load again?
Right. So there's two ways you can produce tokens, or the 𝐃𝐿 cache for a token. You can just produce it from scratch by computing it from the underlying like token IDs, which are tiny. Or you can previously have produced it and stored it in a memory somewhere. Yeah. So the cost ratio is really talking about the ratio between those two mechanisms of producing it. A cache miss means you've deleted it from all your memories and you have to recompute it from the tokens directly. In fact, you can maybe even take that a step further and think about which memory tier do you store it in. So you could store it in HBM. There are other slower and cheaper memories than HBM, like DDR on your host or flash as well. And so one of the things you can do is a calculation of where it makes sense to be in each memory tier. And this is related to how long you're going to store for. So we want to look at the cost of storage in a few different memory tiers and also the cost of rematerialization. So remat means the cost to rebuild all of the 𝐾𝐿 cache from scratch, after you deleted it. So we rematerialize it. And so basically this is going to cost the length of the context. Actually, we'll look at cost per token so that we don't need to carry around this length of context everywhere. So to rematerialize one token of 𝐾𝐿 cache, I need to run a forward pass on the whole model, and then so this is going to be the compute time. I have to rerun the compute at whatever speed my GPU does it, and then I multiply it by my GPU dollars per second.
Sorry, extremely naive question. Why is there not a quadratic term?
Yeah, so there is a quadratic term. It shows up in the compute. As an approximation, I chose to remove it. I'll just show you sort of quickly what that looks like. It's because, so you have the, if you look at the cost per token, or the number of flops per token, there is the flops that are coming from doing the weight matrix multiplies as a function of context length. And then there is the number of multipliers that comes from doing the 𝐾𝐿 cache, which goes up linearly with the amount of stuff you attend to. The slope on this is so low that when you draw it like this, it's very well approximated by a flat line. So it starts to you start to notice the effect of the quadratic or the linear term up in the millions of tokens or so. So just not super relevant.
So what is the reason that there's no company which has over 1 million token context length? If this is true?
Yeah, so there are two costs of long context. One is the memory bandwidth cost, which we've spent a lot of time analyzing. That's this thing. And then the other one is the compute cost. The compute cost is almost always, and sort of actually forced by fundamental principles, to be a much smaller slope than the memory bandwidth cost. And so the primary thing that limits you to have really large contexts are memory bandwidth and memory capacity, which is exactly this effect.
And so there's this idea that Dario said on the podcast and others have said, which is we don't need continual learning for AGI. In-context learning is enough. And if you believe that, then you have to think that we had to get to 100 million billion context length to have an employee that is the equivalent to working with you for a month. Now, maybe that's no longer true as far as attention or something.
Yeah.
But if you think that, then some ML infra thing would have to change to allow for 100 million, the memory bandwidth to allow for 100 million token context lengths. I
mean, sparse attention gives you a get out for sure, because you get this square root, it gives you a big improvement. But I think it's if you look at the history of context lengths of models, from earlier models like GPT-3, maybe to GPT-4, I don't remember when the transition happened exactly. They shot up from about 8K to 100K, 200K. And then for the last year or two, they've all been hovering around there.
Yeah.
I think that actually indicates that is sort of the reasonably balanced cost point, and going massively beyond that would be cost prohibitive.
Not because of the compute cost, but because of
the memory bandwidth cost. Yeah. So I actually don't see a very good path to solving that. Like the HBM is it's at where it is. It's not getting hugely better.
And why doesn't sparse attention solve it?
Sparse attention is a big improvement. Maybe that is priced in already, perhaps. It's not an infinite improvement, because if you go too sparse, you lose too much quality.
Yeah.
But yeah, I mean, the empirical result is that the context lengths haven't been increasing that much. And I think it's because there is no solution to the memory wall here.
Interesting.
Like, so going too sparse just means like you're attending to a very small subset of the tokens, and the quality will get worse. Yeah. So what is the cost of these different ways of producing resynthesizing the KV cache? Computing it from scratch is based on my GPU time. I have to do a certain amount of multiplies in order to of GPU time that I spend in order to produce it. Storing HBM. This really goes as my, I think I had a number here, which was the bytes per token. So I need to have some number of bytes per token. And then I need to store this in the HBM. So it's going to use up some of my HBM capacity. So a way to think of this is that, like, if I have too many of these things sitting in my HBM, like if I fill up my HBM with just KV caches that I'm not using, I can't use that GPU. And so how do I price that? Maybe I say that the cost of it is proportional to the fraction of the HBM I'm using. So there's also times GPU dollars. And then let's just do one more memory tier and say something like DDR, store in DDR instead. The same kind of thing goes up for Flash and for DDR. I put these in the wrong columns, actually. I meant to make two columns. The distinction I want to make is that there is the time to cost to retrieve, and then there's a cost to store, cost to hold on.
Yeah.
And so this is a cost per second, whereas this is like an instantaneous cost. So rematerialization has a cost to retrieve and has zero cost to store it because we've deleted it. This is the one that I put in the wrong location. This is actually the cost to hold on. So I will rewrite it. Okay, so we have, this is the, like if we're just storing it in HBM, it has this sort of cost profile. And then if we store in DDR, it's actually going to take some time. So it's like we get the same thing here, bytes per token over DDR capacity times DDR cost per second. But now this has a cost to retrieve that is higher than the HBM because we need to copy it into the HBM. And so this is bytes per token over DDR bandwidth. And then this consumes some amount of the DDR as well.
And every scale up has DDR and Flash?
This is really a deployment question, and so you can choose that. NVIDIA does deploy in this form. It has both.
Why isn't the cost to retrieve HBM the memory bandwidth, or the bytes divided by memory bandwidth?
Yeah, I mean, it depends what you define a retrieve to be. Here I'm defining retrieve to be move it into HBM so that you can start actually doing inference on it. And so, like, sort of by definition.
And because if it's already in HBM, you can be doing compute while you're getting it from HBM to SRAM?
Yeah, for example. Okay. Yeah. So these are three things, and I guess I ordered them wrong. In general, if you're balancing two costs and you've got different memory, different tiers in the memory hierarchy, you should expect as this cost goes up, this cost should go down. So you can kind of see where the zeros are, and like I should have ordered them. This one first, this one second, and this one third. So if you're going to hold on to it for a very short amount of time, then the all of this is like multiplied by the hold time.
Yep.
This one is, and so is this one.
And interestingly, they have different prices to write for, and as you specify this in the API, for 5 minutes versus an hour.
Yeah,
which suggests that the 5 minutes is HBM and the hour is DDR.
I think that's I think that's a pretty good assumption. It could, if you look at the numbers, it might also turn out that it's one tier down and it's DDR versus flash.
Okay, interesting. And the price difference, I think, was, I'll look it up. Okay, so the base input tokens is 5 per million tokens.
Base, which means remat.
Yeah, that's 5.
This is $5.
To like retrieve, quote unquote, and then the to write to presumably HBM, write for 5 minutes is 6.25.
So actually, we might actually be able to determine the which memory tier it is by the durations. Actually, the durations probably tells it to you. Actually,
and so the 5 minutes versus 1 hour.
Yeah, exactly. I think this will probably end up being it's going to be the drain time of the memory tier that you're in, and so what that means is like given that I know I'm going to be holding something for 5 minutes, I would like to pick a memory that I can read every 5 minutes. Like I can read the whole memory once per 5 minutes, ballpark. So that is the drain time of the memory. So if I take the storage capacity over storage bandwidth, I would like this to be like equal to 5 minutes or something like that.
Mm-hmm.
And so actually we did this calculation for HBM. For HBM, we know that this number is 20 milliseconds. So HBM is much too short, like much too small. DDR could be about an order of magnitude or two off from this. And so this is probably in the order of like, actually, I think it might even be in the seconds, like 1 to 10 seconds. And then this is really, I don't have these numbers memorized, but generally as you go to slower tiers, flash is plausibly in the order of 1 minute. And then like spinning disk, which is massively different, I think is on the order of 1 hour. So this might actually identify that the tiers are probably flash and spinning disk.
Sorry, why is this the calculations? The storage cap divided by the bandwidth?
So you've got a bunch of different memory tiers, like we've listed 4 of them. Your choice of which memory tier is like you want to minimize the cost.
Yeah.
And so you are like, what fraction of the device are you using? You're using some fraction of the device for the holding onto it, and then you're using some fraction of the device to retrieve it. And so let's say I'm using like 10% of the device, and I want to equalize those two fractions. That's a sign that I've hit the right thing. So let's say I've got some runtime here, like I'm going to hold on for all of this time, and then, so this is the time hold, and then there's going to be some amount of time here, which is time retrieve. Mm-hmm. And I want, basically to equalize the costs, these two costs, I want the retrieval time to be equal to the hold time times the like fraction of capacity.
Mm-hmm.
Because like this is the retrieval time. This is how many other things I can hold simultaneously.
Yeah. Basically, just like, hey, you want to store things in there for so long such that the amount of time it's in there is kind of the time to get all your things in there and out.
Yeah, basically.
Makes sense.
I think that probably indicates that this is the 2 tiers of flash and spinning disk. I'm kind of shocked to see spinning disk being used at all because it's such an old technology.
Yeah.
But yeah.
I mean, it's also crazy that it's so slow that it takes an hour to load its full capacity into it, and then
like it's a really unattractive technology, but it's useful in some places.
Yeah. So we're sitting down because I want to ask you some questions that I guess don't need a blackboard. You have this extremely interesting blog post where you talk about how, at a high level, the architecture of different cryptographic protocols looks a lot like neural networks. And there's this convergent evolution where they both need to jumble information across all their inputs. For cryptographic protocols, it's to make sure that there's like each new input into a hash function will totally scramble what happens. For neural networks, of course, they need to consider how this piece of information changes what you should make of this other piece of information. And that has an extremely interesting point. I guess at a high level, the difference in what they're trying to do, in some sense, they're trying to do the inverse thing,
Right.
which is cryptographic protocols are trying to take information which has structure and make it look indistinguishable from randomness.
Yeah.
And neural networks are trying to take things which look like random, protein sequences, DNA, garbled text, and extract higher level structure from it. So they have similar high level mechanisms, but they're actually kind of trying to do the opposite things. I wonder what you make of that.
Yeah. So I mean, the mixing, I try to look for other examples where mixing, like scrambling mixing, shows up as well. There's actually almost even like a physical example where like you're stirring something, you're making a cake and you want to stir the batter, and like literally the idea, like first stir it this way and then stir it this way is like actually not too bad of an approach. But beyond that, like back to the digital world, there are some differences, and the one you call out is a pretty strong difference. The way it shows up, like what makes neural nets, like if you just randomly initialize a neural network, actually maybe it's a reasonable cryptography, cipher as well, because like the random initialization is going to jumble stuff in a complicated way. It may even like do what you want, who knows. The thing that makes it interpretable is the gradient descent. So you can differentiate a neural network and get a meaningful derivative. And we do a lot of work to like not overcomplicate the derivative. So the residual connection keeps it like contained and simple. And so does like the layer norm stuff that we do. One of the biggest attacks against cryptographic ciphers is also to differentiate the cipher. Ciphers run in a different number field. They run in the field of two elements, so just binary, whereas neural nets run like in theory in the field of real numbers. And so you have to differentiate with respect to like binary numbers. But you can absolutely differentiate a cipher, and this is called differential cryptanalysis. And like basically what it says is that if you take a small difference of the input, how like it's quite difficult to make the difference of the output be small. Like the whole job of a well-designed cipher is to make the difference in output very large. So I guess the distinction is that the optimization goals at that point are about complexifying. They don't have the same residual connections or like layer norms. That would,
yeah. I mean, I guess a place where the two merge is backdoors. Okay, so with a backdoor in LLM, you're trying to hide, what do you consider an input? It's not an input into the forward pass, but it's an input into the backward pass. But you're trying to hide an input into the backward pass.
Like this is like an adversarial context. Yeah. So yeah, I mean, in fact, this is actually a place where you get exactly the sort of avalanche property that ciphers have as well. Like adversarial attacks on typically like image classification models, right? Can I find a perturbation of the image a very, very small perturbation of the image that totally changes the classification, totally changes the output. That is the common case in ciphers, whereas that's the like undesired case in neural nets for sure. Yeah.
Okay, so I was asking you, have neural networks actually been used for cryptography? And we realized it might be better to just do this on the blackboard.
Yeah.
So I'm curious, are they actually being used for cryptography?
Yeah, so using neural nets for cryptography, well, in general, cryptography, like creating a new cipher is a very, very dangerous proposition. Yeah. Like almost all of them are broken, like 99% of them are broken. So probably a bad place to start. But the other direction has been very, like in at least one very clear case, quite productive. So there's this construction a construction that exists in ciphers and then was imported into neural nets called a Feistel cipher, Feistel network. So the idea is that you may have some function f, which is not invertible. but you like the function because it like does interesting things, like it does an MLP, for example, or it mixes it in an interesting way. You'd like to build something out of this that is invertible. So the construction we're going to make is going to actually be a 2-input function rather than a 1-input function. And we're going to apply f of x. We need to actually remember what x was. So we're going to stick x over here so that we can work backwards. And then we also can't drop y. So we're going to remember y, and we're going to add them together. And so we form this tuple. So the way to invert this, like if you think I have this output and I want to recover x and y, well, I can easily recover x. That's right there. I just read it off. And then to recover y, if this thing was called z, I can recover y by z minus f of x, because I've already recovered x. So that means that this construction is invertible. This was used in ciphers like a ton, still is used. It's one of the main mechanisms of constructing ciphers. Often you want ciphers to be invertible, especially the layers of ciphers you want to be invertible because that has better cryptographic properties. This has actually been ported over into neural nets. There's a 2017-18 paper called RevNets, Reversible Networks. And what it does is it actually makes the entire, like you can apply it to any network, like a transformer network. You can make, I do a forwards pass, but then I can actually run the entire pass backwards as well. So the whole neural network is invertible with exactly this construction. And so this paper, Reversible Networks, like applied to some layer, like a transformer layer, for example, we've got this function f, which is our transformer layer. Now, normally we would have just an input and then a residual connection coming out. And it gets added like this over here. Mm-hmm. But now the variation of this is going to be, we've got 2 inputs, x and y. So we've got x and y inputs. X goes through the function, gets added to y. And then this becomes the new x, the output x. And then this x becomes the output y. So really what this is doing, this is actually sort of doing, if you think of 2 layers back, this is actually the thing you mentioned before. It's actually doing the residual connection from 2 layers back. Like this y came from the previous layer and was the residual connection there. But because of this construction, the whole thing is invertible. Why do I care? What does invertible matter for? The big thing that it can be interesting for is for training. If I think of a forward passive training, so I will, let's say I have 4 layers, I run them in 0, 1, 2, 3 order. I have to write all of the activations to HBM. And so I get an HBM footprint here that is kind of like linear in number of layers. Yep. So this actually can be the largest memory footprint during training. And so this is normal training, and then I run the backwards pass and I read it kind of in reverse. Like I run them sort of forward pass goes forward, backward pass goes backwards, and I have to read them back out. The idea of this RevNets paper is that because it's invertible, I don't need to store this at all. I can completely rematerialize it when I'm running my backwards pass. So I run my forwards pass, and then when I'm running my backwards pass, I'm simultaneously in lockstep undoing all of the forwards pass steps that I did in order to have the activations that I need here. So this ends up being a memory saving, which is a nice idea.
Interesting. And in some sense, you're spending more compute to save memory.
That's right. Yeah.
Interesting. Huh. Actually, it's kind of the opposite of what you're doing with the KV cache. The KV cache, you're spending more memory to save compute.
Yeah. Spending more memory to save compute is generally profitable given where hardwares are today.
Yeah, interesting. Cool. That was super fun. Right. Yeah. Thank you so much for doing it. I feel like it really vindicated the vision behind the studio and the blackboard. Cool. Thanks so much for doing it.
Thanks.